Good day. We are from Group 4. My name is Agaran and my matrix number is 206455. So today we are going to discuss about combined open and closed section beam. So I'll be discussing about the bending, which is example 19.1. So let's look at the example question. So the question states that determine the direct stress distribution in the wing section shown in figure 19.2 when it is subjected to a bending moment of 5,000 Newton meter applied in a vertical plane. So we can look at the figure. So the beam section has the x-axis as the axis of symmetry. So Ixy equal to 0 and My will be 0. So normally we will use the general equation to find the direct stress. So when My is equal to 0, we will simplify the equation and we'll get much simpler equation, which is Mxy over Ixx. And to solve this equation, we need to find Ixx first. There are three parts of structures in this figure, which is the semicircle, the rectangle, and also two arcs. So first we'll find the second moment of area for the semicircular section. So if we calculate, we will get 0.4 times 10 to the power 6 mm4. And for the rectangular part, we will get 2.7 times to 10 to the power 6 mm4. And for the both arcs, which is arc 2, 3 and arc 4, 6, we will get 0.3 times to power 10 to the power 6 mm4. And if we substitute all together, we will get 3.4 times to 10 to the power 6 mm4. So now we will use the second moment of area to insert in this simplified equation. So now if we look, we will just substitute it. So we will substitute 5,000 times 10 to the power of 3 over 3.4 times 10 to the power of 6 times y. So we'll get 1.47y. So in the part 0 to 1, so the direct stress 0 to 1 will be 1.47 times to 50 sine zeta. So we'll get 73.5 sine zeta. So when the zeta is equal to 0, our direct stress from 0 to 1 will be 0. When the zeta is 90 degrees, our direct stress will be positive 73.5 Newton per millimeter square. And also in the part from 7 to 1, our direct stress will be 1.47 y. So when y is equal to 0, our direct stress will be 0. When y is equal to 50 millimeter, our direct stress will be positive 73.5 Newton per millimeter square. So by inspection, our direct stress from 1 to 2 is positive 73.5 Newton per millimeter square. And the direct stress distribution in 82 and 71 is the same. So, and if we look at the section 3.2, our direct stress will be 1.47y, which will be 1.47 times to 50 sine theta. So when theta is equal to pi over 4, our direct stress will be positive 52 Newton per millimeter square. So now we have covered the upper part of the shape on the x-axis. So the below part will be symmetry to the upper part. So that's all from me. Thank you.
Okay, Assalamualaikum. My name is Muhammad Ridwan Shah, and I'm gonna be explaining about the example 19.2. So from the question, this is the diagram, and then for the thickness of the system is 2 mm. So we're gonna start. We're gonna calculate the shear distribution. So firstly, we need to calculate QS. This is the general equation, and then to calculate the general equation, we need to get the IISS. But before we calculate the IISS, we firstly gonna calculate the Y bar, which is this one. So to calculate the y bar, we're going to use this one, which is y bar times summation of boom area, and then equal to boom area a summation of boom area times y bar. So this one is 100 mm, and then times 4 because of this first, second, third, and fourth. So times 2 because of the thickness, and then plus 200 is 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 so times 4, and then times 2 because of the thickness. So then this part is the summation of boom area multiplied by y bar. So and lastly, after calculating, we're gonna get y bar is equal to 75 mm. So then after that, we're gonna calculate the IXX. So the IXX we gonna calculate within 4 area. So 4 parts. So first part is at this point, and then the second part is this, and then this one is third, and then this one is fourth. So first part is this one is high, and then this one is base, high and base. So the high formula is 100 or 3 times 2 for the thickness, and then plus 2 for the thickness, 125 to the power 2, 25 because of this below center. So then we calculate, and then the point 2 is 400 times 2 times 75 of 2 plus 200, 0.3 times 2 times 1 to 5, the distance, tip of 2, the height. Then 0.3, so and then no, this is 0.4, and 0.1, 0.4 is the open system, this one. So the other is closed system. And then after that, we're gonna get IXX equal to 14.5 times 10 to the power 6. So after getting IXX, we can calculate the QS. So after we simplify the general equation, we're gonna get QS negative SY over IXX in this form. And then we can calculate starting with first Q 0.1 to 0.2, which is this one. And then this 2 is for the thickness. And then this one is from this, which is S1 moving upward, so positive. And then minus the from the 0.1 to the center, which is negative 25. So then after creating, we're gonna get this one. So if S1 is 25, then Q from 0.1 to 0.2 gonna be 4.3. So then based on the Q from 0.1 to 0.2, we get the Q2 is equal to negative 34.5. So after getting Q2, we can calculate the Q from 0.2 to 0.3. So use the same from the general equation. So 2 is like before, thickness, and then times 75 because from 0.2 to the center is 75. Then minus Q2, which is 34.5. And then we get like this, and then we know that in wall 2 to 3, this part which is at 2.2 is negative 34.5, and then at point 3 it is negative 138.5. So then if you're going to calculate Q from point 3 to point 4, we need to actually need to plus. So plus Q3, and then like we do in Q point 2 point 3, we plus Q2. So we need to calculate like Q from point this one, point 0 to point 3. So then we calculate using the general equation. They will simplify, and 2 is the thickness, and then 75 is the 75 above the center of the whole system. So we get like this, and then we plus both at 3 in wall 2 to 3 and wall 0 to 3. So wall 0 to 3, we know that it is negative 104. So by adding both, we're gonna get it negative 242.5. So we can plus it to get Q from point 3 to point 4 using the general equation. So this 2 is always the thickness, and then 75 minus S4, which is S4 is moving downward, and 75 still above the center. So and then we get like this, and then is if S4 is 75, then Q from point 3 to point 4 gonna get negative 281.7. So and then Q from point, let's see, we calculate Q from point 9.4, which is using the general equation, and then 2 is the thickness, and then negative 1 to 5 because it is 1 to 5 below the center. So lastly, we're going to calculate like this, and then based on the example, we get the shear flow. It's gonna shear distribution look like this. So that's all for me.
Hello, Doctor. My name is Muhammad Faisal bin Bahrudin, and my metric number is 203137. And I am from Group 4 together with Ridwan and Agaran. Now I'm going to explain example 19.3, which is done by me. The question is about a wing section that shows below this diagram here. The given value is torque with 10 kilonewton per meter, and G is 25,000, and the wall at 1 to outer is 900 mm. The wall outer from 1 to 2 is around here. From 1 to 2 outer is 900 millimeter, and the nose cell area is 20,000 millimeter square. As you can see, the thickness is 1.5 here and 1.5 here for 1, 2, and then 1, 3 is 2 millimeter, the thickness, and 3, 4 is 2 as well, 2 millimeter. And the length is 300 millimeter, and bottom is 600 millimeter. And the question is to solve for angle of twist per unit length and also the maximum shear stress. So first of all, to find the angle of twist, we have torsional rigidity, which is CG. The total torsional rigidity is for closed section and the open closed section. For closed section, we find the torsional rigidity using the formula given here. We insert the value from the question, 900 and 300 from here and here. And then we get the value is that we get the value for the closed section here. As for the open section, we use the formula here. Also with all the value given, 900 is the sum of 300 and 600 here with the thickness, and we got the value just below. For the total torsional rigidity for the complete section, we add the closed section and the open section, and we get the value 12,006 times 10 to the power of 7, then we move the square. And the torque that is related to the angle of twist, rate of twist is given by the formula below. We can manipulate the formula to the angle of twist per unit length, such here, and we get the torque over torsional rigidity, which we found out earlier, and we insert the value, we get 0.0002 rad per mm. And the 10 power of 6 is here because we convert from meter to mm. Per kilo is 10 to the power of 3, and from meter to millimeter, we add another 10 to the power of 3, which we get 10 to the power of 6, and we got the value here. Moving on to the next one, to obtain the maximum shear. To obtain the shear flow in the closed section, we have these two formula from the textbook 8.18.1 and we substitute E side and we get Q for closed section, the shear flow, which given that by the formula here, and we insert the value based on what we obtain, and we get 250 Newton per meter. As for the maximum shear stress in the closed section, the formula is that shear flow divided by the thickness. So we divide 250 by 1.5 for a closed section. Here, that's the thickness, and we obtain the value 166.7 Newton per millimeter square. As for the open section, we use the formula given here from 18.10, and then we get the value 10 Newton per millimeter square. And that is the solution for this example. Thank you very much.